Hey everybody, we're going to continue our discussion of combined and conditional probability, but we're going to emphasize looking at special circumstances in which we have mutually exclusive and independent events. Our EQ for today is if A and B are mutually exclusive and A happens, what do you know about B? So really this is just an extension of the definition of mutually exclusive that we'll touch on here in just a moment. Now, imagine you're going to play a really simple game with your little sibling. You tell them that if they flip a fair coin and get heads, then they win. If they get tails, then you win. Simple enough, right? So they flip a coin and hide the result from you. When you asked what the outcome was, they simply answer both. That seems like a typical 4-year-old thing to do, right? Does this make sense? Of course not. And don't give me that nonsense that it could land on its edge. We all know that can't happen. This does not make sense because the coin must land on either heads or tails. There is no way that we can have it land on both heads and tails simultaneously. This is what we call mutually exclusive. And so formally we can define it in a couple of ways. And the formal definitions are actually pretty simple. So we say that two events cannot both occur. And that's one way that you can word the definition of mutually exclusive events. Another way we can think about it is that the intersection is empty. Let's look at an example to try and articulate what we mean when we say the intersection is empty. Consider the universal set 4, 5, 6, 7, 8, 9, and 10. So just a few numbers, and let's randomly select one of those numbers from the universal set. A is going to be the event the number is prime. B is going to be the event the number is even. Okay, so let's go ahead and first of all identify which ones are going to be A, and the prime numbers are going to be 5 and 7, and then let's go ahead and define with blue the event B, and those are going to be the numbers even are 4, 6, 8, and 10. Okay, so notice that we're missing one. That's okay. That's actually kind of normal. Let's go ahead and draw a Venn diagram and start putting these things into place, and you'll see why we didn't underline the number 9. Okay, so we've got A and we've got B, and we've got B. So remember that this intersection here has to satisfy both the conditions for A and B. So I'm going to be thinking about that as I go through and put these numbers in their proper places. We'll start with B, the event that a number is even. Well, 4 is even. It's definitely not prime. Same thing with 6, 8, and 10. So there's nothing that's really there in the overlap. Now let's go ahead and take a look at A. The events we had, or the numbers that we had to satisfy that condition, were 5 and 7, but 5 and 7 are not even, so there's not going to be anything in the intersection. And the last one we have is the number 9, but the number 9 is not prime because it's divisible by 3, and it's also not even, so that hangs out here with our universal set. Now we say, what do we notice about the intersection in this scenario? It's empty. So what does that tell us about the probability that a number is both prime and even? We have 1, 2, 3, 4, 5, 6, 7, 8 total outcomes possible, but none of them satisfy that. Thus, P of A and B is equal to 0. And this is our mathematical definition of independence. So mathematically, I'm sorry, not independence, of mutually exclusive events. Okay, A and B are mutually exclusive if P of A and B equals 0. And that is our formal mathematical definition of mutually exclusive events. So the next thing we want to talk about, the next special kind of relationship, is one that is known as independence. Okay, so with independence, what we can say, we define that as when the occurrence of one event does not change the probability that the other event will happen. Now, this sounds a lot like the event A happening causes the effect of B, or moreover, if they're independent, A affects B in some way. And it's very common for students to start thinking about this in terms of cause and effect. And actually, that's not really true. Cause and effect has a different type of meaning. But these two things, independence, are related to the word association, and we'll address that a little bit later on in the course. Okay, so just so you know, this is not the same thing as cause and effect. Don't confuse the two. Here's how we define independence. If the probability of A given that B happens is the same thing as A, then the two events are independent of each other, right? What you can think about is, what this is saying is, all right, A happens given that B happened, but it's the exact same thing as if B didn't happen at all, right? So if the event B does not change the probability of A happening, the two events are independent. But on the flip side of that, you have to also flip it around and say that the probability of B given A, P of B given A is equal to the probability of B. So changing the order is going to be a requirement for independence as well. So if not only P of A given B is equal to P of A, then also P of B given A is going to be equal to P of B. Then if those two things are both true, then A and B are independent of each other. Now, that seems like a weird and kind of frustrating formula to work with as far as the definition goes, and we'll get to that in a moment, but let's go ahead and look at it intuitively. Okay, so first of all, toss a coin. The events of the outcomes are H or T, right? And so the probability that we toss a coin and we get heads is very simply 1/2. Now, you toss a coin again. So we want to know what's the probability of getting heads that second time, right? Given that we got heads on the first one. So if you toss a coin, you get heads, we know that's a 1 out of 2 probability. But if we toss a coin that second time, did the fact that you got heads on it the first time change the probability of getting heads the second time? And the answer is no, right? So since the probability of getting a head on the second toss, assuming we got a head on the first toss, is exactly the same as the probability of just getting a head no matter what, whether it was 1, 2, 3, 4, 5, 6, or 7, or 8 tosses. Notice this is not the same thing as the probability of I get 2 heads in a row. Not the same thing. This is saying, assume you toss a coin and get heads. Does that change your probability of getting that heads on the next toss? We know the answer to that is no intuitively. We understand that intuition to just say, no, these two things are independent. One coin toss does not change or impact the second coin toss at all. Let's look at another example. What is the probability that I draw a red card from a standard deck? So there are 52 cards in a deck, and 26 of them, half of them, are red. So what's the probability that we draw one card and it happens to be red? That's 26 out of 52. So now we're going to assume that this happened, right? We have 26 out of 52, but we drew one of those cards and it's red. Now I draw another card and it also happens to be red. So what's this probability? Assuming that the first thing happened. Well, if we draw one card, how many cards do we have left? We have 51. Now we take a look at, well, what about the next part? How many red cards do we have left? We knew we already drew one of those 26 out, so we must only have 25 left. Now, are 26 out of 52 and 25 out of 51 the same? No, they are not. Since they are not the same, we would say these two events are not independent. What you draw on the second card depends entirely on what you draw on the first card, right? If you draw a card from a deck, it happens to be Ace of Spades, you know there's no way you can get an Ace of Spades again on that second card, unless we have a scenario like we see in this next example. What is the probability that I draw a red card, put it back, shuffle, then draw another red card? So again, now we have a 26 out of 52 drawing a red card in the first place, right? But we take that red card, we put it back in the deck. So now we still have 52 cards and 26 happen to be red. We shuffle it all up, we draw a card at random, and we still have 26 out of 52. And in this case, since the probability of getting a red card on the second draw is exactly the same as if we were to just get the probability of drawing a red card in the first place. Thus, these two events are indeed independent of each other. And we don't really have to do much mathematically to just understand that. This is a very common thing that we can see, especially in working with tree diagram kind of problems. There's a big connection between independent and not independent events. If you are drawing things with replacement, then they're going to be considered independent. If we are drawing things without replacement, then we are going to say they are not independent, right? We put something back, we can consider it going to be independent. If we don't put it back, not independent. Let's look at a couple other practice problems before we head out for the day. Okay, consider the universal set U, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the natural numbers between 1 and 10 inclusive. Consider the events G to be a random number from the universal set that is at most 6. And then H is going to be a random number that is at least 7. Draw a Venn diagram to represent this situation. Okay, let's do that. We'll draw our Venn diagram. We only have two events, so it's pretty simple. Okay. And what we want to see here is part A, or I'm sorry, not part A. We have event G and event H. What I'd like for you to do is start to place these in the Venn diagram, the numbers that are at most 6 and the numbers that are at least 7. And answer this question: are G and H mutually exclusive? Once you've placed them, go ahead and unpause your video and let's take a look at practice problem number 2. Okay, practice problem number 2, we have the numbers 2, 3, 4, 5, 6, 7, 8, 9 are each written on identical pieces of card and placed in a bag. A card is selected at random from the bag. Let A be the event an odd number is chosen. So A is going to be odd, and then B is going to be square number is chosen. So a number that we can take the square root of. Okay, so let's again draw a Venn diagram to represent this situation. This time we'll actually fill in all the blanks. Okay, so here in the event A circle, we have the odd numbers, and I'm going to place them, but I might erase something here in a moment. So we had 3, 5, 7, and 9. In the event B, we had the numbers that were perfect squares. So what numbers are perfect squares? We had 4 is a perfect square, and 9 is a perfect square. Now here's where I said I might want to erase some things. Do I have any numbers that show up twice? And indeed in this case I do. So what does that tell me? That means 9 needs to go in the middle. Okay? What numbers are in our universal set chilling out here? What did we not take care of? Well, we took care of 3, 4, 5, 7, and 9. Now we need to place 2, 6, and 8 all by their lonesomes out here. Okay? So there, we've drawn a Venn diagram to address that situation. And now we want to try and see, let's determine whether A and B are independent events. Okay? So if A and B are independent events, then what we can say is the probability that A given B is equal to the probability of A on its own, and P of B given A is equal to probability of B on its own. Let's try and figure this out. Alright, so instead of using our formulas too much and really diving into the mathematics of this, let's utilize the Venn diagram, because the Venn diagram can be a really powerful tool for us. Okay, let's do it the easy way. So the first thing we want to see is probability of A given B. So since it's given in B, we're looking at what's the probability that from circle B it is also in circle A. And in that case, the only element there is 9, right? So what that tells me is that we have one element, 9, to represent the probability of A given B out of two total elements, 9 and 4. So that means the probability of A given B in this case is 1/2. And we want to know, is this the exact same thing as if B doesn't happen at all? Is it the same thing as P of A? right? This is not really intuitive for us to understand, just by saying, well, is a number being prime independent of, or a number being odd independent of a number being square, right? So let's go ahead and try and figure this out and see, are these two things equal? Well, now, what's the probability that our randomly selected number is just in A? Okay, well, there are 4 elements here out of a total of 8 total numbers, right? 2 through 9 is 8 numbers. So that means we have 4 of them that were in circle A out of a total of 8 numbers. And are these two things equal? Yes, they are. We're halfway there to proving independence. Let's do the same thing now by looking at probability of B given A and see, is that the same thing as if A doesn't have B at all? Okay? So we do the same thing. We're looking now at what's the condition. The condition or the given is the number must be from A. It must be an odd number. Now, of those odd numbers, how many of them are squares? And that's 9. 9 is the only of those square numbers, right? So, in that case, we have 1 element out of 4 that fit this description, right? Now let's see what elements in general fit the description from this universal set that are square numbers. Well, probability B, there are 2 numbers that are square, right? Out of those, and there's 2 out of a total of 8 numbers. And are these two things equivalent fractions? And they do happen to be. What does this tell us? Well, we've satisfied the first part of the independence condition, the probability of A given B equals probability of A, and we've satisfied the second part of the condition. Thus, A and B are independent of each other. We can interpret that by saying the following. The fact that we might choose an odd number from this bag is independent from the fact that we might choose a square and vice versa. That's it. Okay? So what we're going to do next in our examples is we'll start to look at more complicated tree diagrams and start to see how these things with independence might be connected to them. We're also going to see a lot more practice with mutually exclusive events, independent events, and more complicated Venn diagrams. Thanks for watching, you guys. Have a wonderful day.